Hey guys, this is me starting to record Exam 3 material, which is about indefinite integrals. If you're seeing this before Exam 2B is over, you don't need to pay attention to this yet. I'm trying to get on top of things. I guess depending on when you see this, you already know whether I got on top of things. I'm planning on putting all of this in one big YouTube playlist and putting breaks where I say, okay, now pause and go do some homework. You don't need to watch all this at once. Let's try this out. Okay, so remember, we did indefinite integrals, and the point of these was that the integral from a to b of g of x gives you the total change in a quantity whose rate of change is given by g of x. This is the way we stated it when we were first talking about integrals in the first place, where we had like a bug moving. We knew how fast the bug was moving. We wanted to know where is the bug, how far is the bug moving. We made that more codified when we talked about the fundamental theorem of calculus, is that if g of x has a derivative, then or has a derivative on the interval a to b, then when you integrate that derivative, you get the original function evaluated at b minus evaluated at a. And this is mostly a restating of the thing we just said, where we know the rate of change, the derivative of something, and we can integrate that with a definite integral to get the total change in that thing over a period of time. Integrating from here to here tells you how much did it increase or decrease by from this time to that time, which this is a way of saying how much did it increase by from this time to that time. And so far, the point has been, I want to understand the original function from the derivative. And at this point, we're sort of taking these things and reversing them and saying, well, suppose I want to know this definite integral. A way of finding a definite integral, if you hand me an integral you want to know, if I could just figure out what the function g is, that it's a derivative of, then I can tell you the definite integral right away. Like this was an explanation for what the integral means. Now I want to interpret this same statement as instructions on how to compute a derivative. Let's get to an example. Yeah, let me define this word first. So, to compute an integral of a function, of some function from somewhere to somewhere, it's enough to find what we're going to call an antiderivative. This is what the rest of the year is going to be about, is finding antiderivatives. Very often we'll use a capital letter for the antiderivative and a lowercase letter for the derivative. And evaluate g of b minus g of a. So this is what our goal is finding antiderivatives. And let's start with an example where it's not too tough to figure out an antiderivative. Let's try to compute the integral from 1 to 3 of x, let's make it 1 to 4, of x squared dx. This is going to be big F of 4 minus big F of 1 if big F is a function whose derivative is x squared. Can we figure out a function whose derivative is x squared? Well, we learned the power rule. The derivative of x squared is 2x, right? And that's the way it works. If I take the derivative of any power of x, I get that number out front, x to the n minus 1. So I think about that for a second, and I say, well, if I want the answer to be x squared, then the exponent of the original should have been 1 higher than 2. I want to think about x cubed. What's the derivative of x cubed? The derivative of x cubed is 3x squared. I'm good at derivatives. I can look at that and just write it down, which is almost x squared, what I want. It's not quite x squared because there's a 3 out front. What would I do to deal with the 3? Well, I also know that a constant out front stays out front. I just need to put a constant out front of this x cubed. If I put a 1/3 out here, then it'll still be there when I take the derivative. The derivative of 1/3 x cubed is 1/3 3x squared. Hey, I got a thing to cancel with the 3. I got x squared. Hey, we did it. We can use capital F of x is 1/3 x cubed. So the thing we want is the integral from 1 to 4 of x squared dx is going to be big F of 4 minus big F of 1, where big F of x is 1/3 x cubed. This is annoying to write. We want a shorthand for writing it. It's a new notation that's not deep. It's just sort of you never had reason to care about this before. We're going to write this as 1/3 x cubed bracket. So when I learned it was bracket and bar. A lot of teachers will do this with brackets on both sides. We'll see other people doing it. I learned it with a bar. Bracket bar 1 to 4. Or occasionally you'll see it written as bracket 1/3 x cubed. X equals 1 to 4. To clarify, what this is saying, this bracket bar thing is saying the stuff inside the brackets, plug in 4, plug in 1, subtract, top minus bottom. Occasionally there will be lots of letters floating around, so I like writing this x equals 1 to 4. This is like an optional, more specific way of saying what you're doing. This should be the integral. Take this function, plug in 4, plug in 1, and subtract. So I want 1/3 of 4 cubed minus 1/3 of 1 cubed. Plug in 4, you get this. Plug in 1, you get this. Now subtract them. 4 cubed is 64. 1 cubed is 1. Over 3. 64 minus 1 is 63 over 3. 63 over 3 is 21. Apparently, we have just by hand worked out that the integral from 1 to 4 of x squared is 21. Is that right? We know how to compute integrals on a calculator. Let's graph x squared. Oh, I've got a pretty good region. Let's calculate the integral from 1 to 4. The answer is 21. Hey, we did it. So that's our motivation. We'd like to be good at computing definite integrals to get areas under curves or understand rates of change, or we've got a couple good reasons to want to know the definite integral. And a way to do that is to find an antiderivative. Our goal is to get good at finding antiderivatives, and we have this notation that we use for that.